So the test signal that we've been looking at so far is the step function. And recall that it's defined by saying some r of t is equal to r for t greater than or equal to t naught, and 0 for t less than t naught. And this is a scaled step function, so we could think of it r times 1 of t, right, where this is the notation from FE. And the Laplace of the step is just r over s. So if r equals 1, then this is a unit step input function. This was good for exciting the system. It's like applying a constant force or a constant torque. And a lot of times we'll also let t naught equals 0. So we're just starting at t equals 0, and we're interested in what's going on. So it's 0 before that, and boom, at t equals 0, takes the value r, or 1 if it's unit step. We can look at what we call a ramp function. And this is a little bit different, obviously, than the step function. The step, again, represents, say, a constant force or a constant torque input. The ramp function, we can define it as r of t is equal to, we usually just use, say, r times t for t greater than or equal to 0, and 0 for t less than 0. Or this can be written as rt times 1 of s, and, 1 of t. Then it has a Laplace transform here, if you go into the tables, of just r over s squared. So the t adds another 1 over s. And so if I plot this, it's just say time here, r of t, and it's just a straight line with slope equal to r. And so this represents, you could think of it as a constant change in the speed, or a constant change in the motor shaft angle, or a constant displacement of the function. As an input, it really has, this is better thought of as displacement as opposed to force. We typically don't like ever-increasing forces like this, but we might want to command ever-increasing displacement. So it depends on what we're, what kind of plant we have and what we're commanding, but this typically looks like a displacement kind of input. Another function, we can essentially just bump up the power of t there, and we can use a parabolic input function. And this would have, if we go ahead and look at what the time domain function would be, say r of t would just be r times t squared over 2 times 1 of t. And this, again, has the same kind of form here. The 2 is there for the Laplace transform, frankly. But we can write this as rt squared over 2 times 1 of, oops, I just wrote that, sorry. But in the Laplace domain, then because of that 1 over 1/2 there, we get r over s to the third. And again, I can plot this, and if I plot r of t versus t, it's just a nice parabola like that. And we can think of this as commanding an acceleration. And it's not a very typical function to use, but it is there. And there is the idea of, say, a function that's like a t to the third, and this represents something like a jerk. If you're familiar with the idea of a jerk, it's a rate of acceleration or change of acceleration. Again, not very typically used, but is there. All of these three will be looked at in the context of what we call regulation and tracking. All right, and we're gonna talk more about those two ideas how we can test the system's ability to regulate or track given these types of inputs to the system.